So last week we talked about general trees and also about binary trees. Recall that a tree in general, um, any node in a tree can have any number of children. So a general tree, a node can have no children, one child node, two child nodes, three child nodes, and so on. There's no restriction. A binary tree is a tree such that each node can have at most two children, so a left child node and a right child node. Now, binary trees are trees, but then there's also a subset of binary trees called binary search trees. So a binary search tree is a binary tree, and here's an example here. So it's a binary tree, meaning that every node has at most two child nodes, but then binary search trees have an additional property, which is that every node in a node's left subtree is less than that node, and every node in a node's right subtree is greater than that node. So for the node 10, every node in this left subtree is smaller than 10, and every node in the right subtree is greater than 10. And that's true for all nodes in the tree. So for the node 6, every node in the left subtree is less than 6, and every node in the right subtree is greater than 6. Same thing for the node 15. There is no left subtree, but every node in the right subtree is greater than 15 and goes all the way down. So for 8, 7 is less than 8 and it's in the left subtree. And for 18, 17 is smaller and 20 is bigger. So if that property holds true, then you have a binary search tree. And again, it means that for every node in your tree, every node in the left subtree is less than that node, and every node in the right subtree is greater than that node. And that's true for every node in the tree. So here's another example. This is a binary tree, but it is not a binary search tree. So it's a binary tree because each node has at most two child nodes, but it's not a binary search tree. Why? Well, there's a node right here that's a problem, 11. 11 is greater than 10, but it's in 10's left subtree. So that violates the property. Okay. There is another problem here, 14. 14 is smaller than 15, but it's in 15's right subtree. So that's also a problem. So these, it's kind of tricky sometimes to spot, but this would not be a binary search tree. It would be just a regular binary tree, but not a binary search tree. Now, there are different binary search trees for the same set of data. So if we look back at this first example, this binary search tree contains the data 4, 6, 7, 8, 10, 15, 17, 18, 20. The binary search tree that contains that data is not unique. Here is another binary search tree that contains that same data. And this is a valid binary search tree because everything in 4's right subtree is bigger than 4. Everything in 6's right subtree is bigger than 6, and it doesn't have a left subtree. So this is a very obviously inefficient, not good, not well structured binary search tree, but it is a valid search tree, and it's a binary search tree that has the same data as this first example that we looked at. So the difference between these two trees is the insertion order, or the order in which the trees were built. So this tree was built first by adding 10, and then by adding 6, and then 15, and then perhaps 4, and then 8, and then 7, and so on. This tree was built by adding 4, 6, then 7, then 8, and so on in order. So the order in which you insert things into a binary search tree matters in terms of the tree that you'll get. Now, for an insertion order, every binary search tree is unique. So if I tell you that you have to insert things into a binary search tree in this order, 4, 6, 7, 8, 10, 15, and so on, you will get this exact tree. And if I tell you you have to insert things in the order of 10, 6, 15, 4, 8, 18, 7, 17, 20, for example, you will get this exact tree. So for every set of data, there is not a unique tree, a unique binary search tree that represents that data, but for every insertion order, there is a unique tree that represents that insertion order. Now, how do we insert into a binary tree? So let's take a look. So we're going to look at an example here. This is a valid binary search tree. So everything in the right subtree of 7 is greater than 7. Everything in the left subtree of 7 is less than 7. Same thing for 8. Everything in its right subtree is greater. If we look at 18, everything in the right subtree is greater, everything in the left subtree is less than. If we look at 10, everything in the right subtree is greater than, and same for 15. So this is a valid binary search tree. And what if we wanted to insert, let's say, 12 into this tree? Well, to insert something into a binary search tree, you basically just do a search. So let's talk about search first. To search a binary search tree, you basically look at each node and you ask, is what I'm looking for less than this node or greater than this node? If it's less than, you go into the left subtree, and if it's greater than, you go into the right subtree. So kind of exactly what you'd expect. So if, for example, let's say I was searching for 15, I would start at 7 and I would say, okay, 15 is greater than 7, so I go right. 15 is greater than 8, so I go right. 15 is less than 18, so I go left. 15 is greater than 10, so I go right. And there it is, I found it. So to search, you again just ask at each node, you ask if your search key is greater than or less than the current node, and then you go in that direction. Now, if I were to search for 12, I would again start at my root, and I would say, okay, 12 is greater than 7, so I go right. 12 is greater than 8, so I go right. 12 is less than 18, so I go left. 12 is greater than 10, so I go right. 12 is less than 15, so I go left, but there is no node to the left, and so that's how I know that 12 is not in this tree. Now, if I wanted to add 12 to the tree, as I mentioned a minute ago, I basically just search for it, and then I add it wherever it would be if I were to have found it. So if I want to add 12, I again just do the exact same search I just did, so greater than 7, greater than 8, less than 18, greater than 10, less than 15. So here's where I'd expect to find 12. So to add it, I just put it in that place. So let's do one more addition. Let's say we wanted to add 13. So I'd start with 7. Okay, 13 is greater, so I go here to 8. 13 is greater, so I go right. 13 is less, so I go left. 13 is greater, so I go right. 13 is less, so I go left. 13 is greater, nothing there, so I add it. And let's add one more. Let's add 5. So 5 is less than 7, so I go left. 5 is less than 6, so I go left. 5 is greater than 4, so I go right, but there's nothing there, so that's where I add it. Okay, so again, to add to a binary search tree, you just perform a search looking for that node, and then you add it where you'd expect to find it. Now, deleting from a search tree can be a little bit trickier. There are kind of three things we need to think about. One is deleting a node with no children. That's actually pretty easy. So if I want to delete a node that has no children, I just get rid of it. If I wanted to delete this 5, I just get rid of it, and what I'm left with is still a valid search tree. But then as we talk about in the notes, the second case is deleting a node with a single child. And if we wanted to delete a node with a single child, and there's an example here, we basically set that parent's node to just be the deleted node's child. So if we want to delete 6, for example, from our tree, 6 has a single child. So all I would do is just delete 6 and make 6's parent now point to 6's previous child. Okay, so that's the second case. Both of those are pretty straightforward. Again, if it's a leaf node, you just delete it, basically set its parent to null. If it's a node with a single child, you just set its parent, new child, to be its child. The third case is if a node has two children, and here when we delete, there are two options. So the first option is to set the deleted node's parent's new child to the deleted node's in order successor or to the deleted node's in order predecessor. So you have to think about the in order traversal of the tree, and then you're setting the parent's new child to either be the in order successor or predecessor. The in order successor is the leftmost node in the right subtree, and the in order predecessor is the rightmost node in the left subtree. Okay, so let's take a look at an example of what this would mean. So let's say we want to delete, let's say we want to delete 18. So there are two options of how we could delete 18. The first option would be to go to the in order successor, which would be the leftmost node in the right subtree. So that means we go into the right subtree, which is 20, and then we go left as much as we can. Well, 20 is as left as we can go, so that would be that option. So we would replace the 18 with the 20, get rid of that node, and you can see now that this is still a valid binary search tree because everything to the right in the right subtree of 8 is greater than 8. Everything in the left subtree of 20 is less than 20. So we've maintained a valid binary search tree. Our other option is to take the in-order predecessor, which means the rightmost node in the left tree. So we go into the left subtree, and then we basically just go as right as we can. So we go right, and then here we hit can't go right anymore. So we basically replace that deleted node with that node. And again, here we have a valid binary search tree because everything in the right subtree is greater than the 17. Everything in the left subtree is less than the 17. So those are the two options for deleting a node. Let's take a look at, let's see, one more example. Let's say we wanted to delete the 8. So again, we can take the leftmost node in the right subtree. So if I go into my right subtree, I'd get 18. Oh, sorry, I have to give 8 only has one child. So let me actually just make this data a little bit different so we can try one more example. Okay, so I've changed our tree a little bit here. It's still a valid binary search tree, right? Everything in 7's right subtree is greater than 7. Everything in 9's right subtree is greater than 9. Everything in 9's left subtree is less than 9. So let's say we now want to delete the 9. So our options again are to take the leftmost node in the right subtree. So that means I go into the right subtree starting at 18, and then I just go as left as possible. So I go left to hit 10, try to go left again, but there's nothing else there. Note that in this picture, it looks like maybe 12 might be the leftmost node, but you find the leftmost node by just going as left as many times as you can. You never go right. You just start in the right subtree and then go left as many times as you can. I can't go left anymore here, so that's it, I'm done. And then I replace that data. Oops. Sorry. And then 15 now becomes the left, sorry, the left subchild of 18. Okay. And again, you can confirm that this is still a valid binary search tree. So again, to delete a node with 2 children, you can either replace that node with the leftmost node in the right subtree or the rightmost node in the left subtree. And to find those nodes, you just go to the first node in the subtree. So if we're going to the first node in the right subtree, then you go left as many times as you can. Or you go to the first node in the left subtree and you go right as many times as you can. So for example, again, if I wanted to delete 7, I would either replace 7 with the leftmost node in the right subtree, which means I go to the right subtree and then I go left as many times as I can, meaning 8. Swap it with 8. Or I replace it with the rightmost node in the left tree, which means I go to the left tree, which is 6, go right as many times as I can, which I can't, and I would replace it with 6. Okay, so there are some examples of binary search trees and an example of adding nodes to a tree and deleting nodes from a tree.